All right, it's basically working now. So the rockets now are in a much better state than they were last time. The new system with the gyroscopic stabilization is working kind of to the best that it can at the moment. So this is the rocket barrel that I launched from. We've got a titanium printed flap. We've got 2 barrels per forearm, so there's gonna be a total of 4 rockets in the suit, at least in the arms, might be more. But all that to say that the rockets work now, so we got something. Quick background on the Mark II rockets. The very first attempt was a finned rocket, kind of taking both your fin stability and gyro stabilization, combining it together, finned rocket, right? Then the next version, which is the one that we're doing now, that one uses a gear train to actively spin the rocket in the barrel, pre-giving it the gyroscopic stabilization before it launches. However, we don't have fins anymore, so our kind of basic fin stability goes away, and we have to rely a lot more on the gyroscopic stabilization, which has its benefits. However, it's not perfect. And then there's a third rocket design that we're working on after this one, and that one takes both ideas, kind of combining fin stability and rotational stability and optimizing both aspects so that it flies better than all the other ones. So today we're going to kind of focus on looking at how we can learn from that design and the gyroscopic stabilization intention of the design and better apply it to the third design, which is the direct drive rocket that kind of combines both of these ideas. Last time we talked about static stability, which is the stability you get from the fins and the center of pressure and center of gravity kind of relation to each other. That kind of lays down our foundational rocket stability that we need in order to actually add on our gyroscopic stability. If we look at the overarching idea behind gyroscopic stability, there's 3 big things we need to think about. The first one is going to be the actual disturbances on the rocket. If we look at the kind of flow analysis from last time, we can actually see how much force is being applied to the rocket to get it to restore back to its original trajectory. And that was one thing that kind of was revealed throughout the center of pressure calculations, is that even though the rocket itself has a good static margin, there's a little bit of deviation in the center of pressure throughout the angle of attack, a little bit of like oscillation, kind of inconsistencies. If you actually look at the forces being applied to the rocket at different angles of attack, you'll see that it's much less than a rocket that has properly designed fins like the other one. So that kind of tells us a little bit that the center of pressure may be okay, but even if the rocket were to deviate from its path, it's restoring forces so little that it's really not doing a whole lot for us, but it kind of gets us in a better position than the other rocket, the very first one. And there's also going to be gyroscopic precession. So what that relates to is the actual behavior of a spinning body when it's acted upon by an outside force. You have your rocket spinning and flying, and then it experiences a disturbance moment. Because of that rotational velocity, what's going to happen is that instead of tumbling, the rocket is going to deviate from that path in almost like a conical motion. And what happens is that as your rocket spins faster, the deviation from its flight path gets slowed down. So that kind of has a little bit of a good and bad side. If a rocket is deviating from the flight path and the fins want to restore it, that restoring speed is also going to be slowed down by the spinning, but it also slows down our disturbance speed. So if a rocket is flying straight and something disturbs it, it'll take longer for the rocket to actually succumb to the disturbances because of the actual gyroscopic precession, which is still kind of connected to the angular momentum and the rotational speed. Like I mentioned with bullets though, they can get away with it because they spin so fast that any sort of deviation in their trajectory, it gets extended throughout the bullet path and it's going so fast that it doesn't even matter. We can't really reach those speeds with our rockets because we're not using rifling and we don't have the same kind of propulsion mechanism. However, what we can do is we can actually dump a ton of energy into the rocket to get it to spin. So you can think any sort of external mechanism spinning up the rocket, which is kind of where this design has been. However, it's been using a gear train. The gear train is a little inconsistent and there's a lot of energy losses from the motor to the actual output. So even though the motor itself, a brushless motor, spins super fast, the actual output is not going to be as fast. It allows me to test it, but the actual kind of performance that I'm looking for is not really coming from that. And the third thing is going to be our spin up rate. So we know that we need the rocket to spin fast, but the actual dynamics behind getting it to that speed kind of varied between our different rocket designs. So kind of backtracking and reanalyzing the gyroscopic stability of all the previous rockets, looking at the finned rocket, that one we know had bad static stability, which is why we never got to see the actual gyroscopic stability in action. But if we look at the fluid dynamics analysis again one more time, we can actually track the tangential forces acting on the rocket that's created from the twisted fins. So with the fins being twisted, the air that flows over them also imparts a tangential force, which would cause the rocket to spin. If we look at the data, we actually get a non-zero value that tells us that the rocket technically would have spun up actually super fast had the rocket flown long enough and straight enough to reach the speeds where that spinning would come into play. But because static stability is off, we never reach those speeds. But what we can also gather from that is we get a spin up rate and we can kind of get a angular velocity of the rocket, which correlates us to an angular momentum. If we look at the angular momentum and we look at our disturbance moments that are kind of created from the angles of attack, what you get is a kind of gyroscopic precession factor, and that kind of correlates more to the angular velocity of the rocket deviating from its path. So a lower value means that the rocket is going to deviate a lot slower. So we're kind of looking for a much smaller kind of gyroscopic precession factor. So with this one, based on the actual forces that we're getting from the simulation and the kind of spin up rate of our finned rocket, we actually get a pretty decent precession factor, which means that it probably would have had pretty decent gyroscopic stability, but we never got to experience it. We can put that to the side now, but at least we know what we're looking for in terms of how we can calculate and do the math behind our gyroscopic stability. So taking that math and kind of applying it to the next two rockets, if we look at the one we just tested, the geared rocket, that one we have to get the spin up rate from the motor itself and the gear train. If we just do a basic calculation down the gear train of like gear ratios and motor speed. We can get an idea of how fast the rocket should be spinning in the barrel and use that to calculate our gyroscopic precession factor. We get a pretty decent value for the geared rocket as well. We know it doesn't fly perfectly straight during the test, but we know it flies better than it does without the gyroscopic stability. So if we look at the very first test of the exact same rocket without spinning it up, we see that it immediately just tumbles and spins and flies into the ground. This one, there's a little portion of the flight path at the very beginning that's a lot more linear than in the past. And that to me provides a much better indication that the rocket is experiencing a little bit of that stability on the way out, but there's no fins to actually restore the flight path, and the rocket's rotational speed slows down as it flies. We're probably losing a lot of that stability very quickly because the actual RPM of the rocket is not super high, and that's kind of why we see that erratic behavior at the end. Also, you'll notice that as the rocket flies and deviates from its path, the thrust is still happening even when it hits the ground. All the math and simulations that we've done evaluate the rocket's condition at its maximum dynamic pressure, which for us correlates to its maximum speed. If we're not able to get the rocket to stay stable throughout the entire thrust curve, then that means we're not going to reach our maximum speed, which means that the data that we're evaluating with doesn't necessarily correlate to the actual rocket condition that we see. So that deviation that's happening before the maximum speed, which means that the rocket is experiencing not enough stability to get it to that speed, which we need in order to properly evaluate our rocket condition, which also indicates a need to improve the stability so that our rocket can be evaluated and tested at the proper conditions that we're doing our simulation at. I might do more tests with the rocket to get better experimental data, because one test doesn't necessarily provide conclusive evidence that the actual system is working the way that I'm thinking. However, the rocket test I'd still want to say is a success, because even though it's not flying super straight and not experiencing the kind of behavior that we want after launch, the entire system to get it to launch worked together. So it was like a triple system integration. The rocket flap worked, the gyroscopic stabilization mechanism worked, and the laser igniter worked. So now if we take all this that we've learned from the first two rockets and apply it to the third one, we already know that one has good static stability from the last video. Kind of the general flight stability is there, and we can build on top of that with our gyroscopic stabilization. And if we look at the motor that I'm going to use to spin that rocket up, we no longer have a gear train. This one sits around the rocket. It's a frameless brushless motor that couples with the rocket itself, so that instead of having any sort of gear, it's one component that meshes with the rocket that allows it to slip through. It's also a lighter rocket because it doesn't have the metal gear like this one does, and that direct drive allows us to spin the rocket at a much faster RPM and have a lot less kind of transmission losses like we do in this design. So looking at the gyroscopic stability, this one has a lot better gyroscopic stability factor, and we already know our static stability is much better. So if we just kind of add these two together, we get a pretty good idea that this rocket's going to perform the best out of all of them. However, we actually need to build it and test it, so that's coming at some point. So I'm kind of working towards this design to now get it up and running and functional, but there's a couple of minor improvements in between the laser igniter and a couple of other elements that are going to happen. So we'll kind of look at those as we progress to this new design, so I can work on it in the background. But it's on the way. It's happening, and we've kind of proven and done all these experiments and tests to tell us that this is where we should be going. Look out for that. It's going to be great. Appreciate all of you watching. We're going now. We got a dub in the books. Rocket launches, a little bit of stabilization going on, so we're going in the right direction. Stay tuned.